So today we're going to do a little bit of introduction to the first project, which is due very soon, but the soonness is just an indication that it shouldn't be too hard. If it is, it's probably a good sign that the class is going to be a terrible experience for you. So take that to heart. If it's super hard, then certainly talk to me about how to go forward. Now, there have been cases where people started off, it was rough, and then they figured things out and things turned out okay. But if it starts off rough, at least make sure to talk to me and make sure so we can make sure that we figure out a path to get you towards success. Nothing worse than going through this class and kind of suffering through but doing poorly on everything, because then you're not going to learn as much as you might if you're kind of more ready for the class. Okay, so this is the class webpage. Some people have asked me where it is. The URL is hard to see here, but it's the best way to find it is just to search for Remzi, and that's me. And then it's right here, and then there you are. So anyway, Spring 18. Make sure to look at the Spring 18. All my class offerings look similar because I've been using the same antiquated web pages for some time. So on here, you'll start to see, soon we'll start populating in when all the different projects are due. Right now, it just looks very optimistic. There's just one project due, but these will soon enough start filling in every week or every 2 weeks. And so the feeling of dread that accompanies that should soon be filling your souls. Here is Project 1A, which is what we'll be talking about today. So what I'll do is I'll first read through the assignment with you so that we can make sure we all understand it. And then we'll look at a few little code snippets that we'll write together, by which I mean I will write and you will watch. And then we'll end the discussion. I'm also realizing that after the first lecture is a 3-hour intense period of time, and the discussion about the project is actually more casual because mostly it's not as conceptual, right? It's like, here's what the project is and here's some code that might help you along. So I may, instead of just having the 3-hour lecture and then this is a 1-hour discussion, I may sneak some discussion in the future into that lecture time as a, hey, I'm exhausted at the end of the night student, so I'd like to be able to sit and just kind of enjoy a discussion. And then I may use this time for a little bit of other lecture. I'm not sure exactly how that's going to go, but that's just a warning to you and I guess to anybody who listens to this. And I'll send mail about that if I do end up doing that. Okay, so let's look at the project. It's right here. It's due Monday by midnight. If you turn it in at 3 a.m., will I notice? No, we're not going to be super strict on things like that. The project is to be done by yourself. There's 2 ways you can really get help on this project if you're stuck on things. A very good way is to, after you have spent some time trying to figure out the problem yourself, like 5 minutes or 10 minutes or something like that, you should always try to debug yourself first before you ask somebody else for help, because you don't want to be, anytime you run into any little problem, needing somebody's help. You want to be able to generally figure out problems on your own. And also you have to realize that other people, even people dedicated to helping you in this class, have a limited time budget. So you don't want to use too much of that for every little problem. So please do try to figure out your problem first, but once you can't, and you know, the amazing thing is Google will help you with everything. I'm having this problem, you type a compiler error or warning into Google and you get a lot of information today from places like Stack Overflow and elsewhere about how to do things. So please feel free to use those resources. The internet, which is like the stupidest advice ever, or most obvious, but there it is. But once you've run out of internet help or you're frustrated or whatever, feel free. One thing you can do is send mail to 537-help@cs.wisc.edu. That goes to me and every person who's assigned to help this class, like TAs and peer mentors, which I'll talk about more in a second. And we try to answer your questions relatively promptly. This paragraph tells you what you should do in order to get help. For example, sometimes people will say, my code doesn't work, and then they'll give a very little other information. This is very hard to help with. What's much better is to give as much information as possible to us so we can look at your problem. So what I suggest to do is put your code in your hand-in directory. We'll talk about hand-in directories and where those are in a second. In fact, it's perfectly normal just to work out of your hand-in directory. Just that's where your code is. Put your code in there. Tell us what that directory is. What's your CS login? cut and paste what you saw on the screen and include that in the email so we can say, oh, when you ran the compiler like this, you type this, this is what it's spit out, so we can see exactly what you are seeing. If we don't see what you're seeing, it's very hard to debug. And if conversely, if we do see what you're seeing, we're very good at debugging because people have the same problems over and over again. We're good at helping on these projects with the problems you're going to run into. Give us all the information. We will quickly help you. Make it hard for us. We'll help you slowly. So just help us by, and therefore help yourself. So that's 537-help. I said the other way to get help is we have an increasing pool of people assigned to and paid to help you in this course. They are these 6 TAs who sent me these various random pictures of themselves. Or ones I found, if they didn't send them in a prompt manner, I found in images on the internet of them. So you can try to figure out which of those I found and which were sent. And so they're going to be around to help you. We also have about nine or 10 peer mentors who are undergrads. So these are all grad students who are undergrads who've gone through this course, did really well, passed a interview with me, and are also going to then be helping you some number of hours. And the way we do all of that help is basically they come to the Linux labs and in the CS building and stand around and wait to help you. Okay? And so all we're trying to do, and we'll be adjusting this throughout the semester, is put them there in hours where you might be there. Now, we had some discussion about this for the initial project, which is due Monday. These are the hours we came up with. I take no blame for these hour choices. They said these would be useful to some people. I didn't know if I believed them, but the hours we went with were basically Friday, Saturday, Sunday, and Monday, 7 to 11. Whether that matches when you work or not, this will be approximate for now, and later we'll base it on polls of you, okay? So we're kind of stuck with this for now. For this first project, you shouldn't need a lot of help anyway. And if the worst case, you have to go Sunday night and get a little help or whatever. I know a lot of you think Friday night, perfect time to start my 537 assignment. So for those of you, this is perfect. And others are like, well, Friday was done. Now it's Saturday, time to work, Saturday night, perfect, etc. Like I said, we'll change these schedules over the semester and we'll base it on your input. We want to match when you need help to when they make themselves available. Of course, we can't do that perfectly because they also have other things to do outside of just helping you. But at least in each of these cases, there will be multiple people in the labs. And like I said, this is just one way to get help. It's the other way is just to send email, which you can get help at any time. The peer mentor hours will also fold onto these, but we haven't set those yet. So the TAs are already signed up for these hours. And what we'll do is I'll send out one more mail about how to get help in the lab. It'll basically say there'll be some kind of process of a sign-up sheet. So when you're there, you put your name down in a sign-up sheet, and then the TAs come find you and help you. And they generally try to help you quickly diagnose at least one problem that you're having and then move on to the next person. They generally can't sit there with you for an hour and help you figure out everything. So try to use the advice, the help that way. Like, oh, I've been doing a bunch of stuff, but then I'm stuck on this one thing. Help me with that. Not I have, a whole mess of problems. Try to just focus on one problem and then allow other people to kind of round robin and get help as well. So any questions about help? And I also answer the emails. So, and then of course, the other thing is I have office hours. I found that the larger this class, there's some sort of inverse property of, have to be careful with cans. By the way, that reminds me of a story which I'm now going to tell. There was a class I attended once, and the reason I attended it once is because on the first day, I sat in the back, and then I, for some reason, put my can of Coke on the ground, and then I soon kicked it over. And then I watched in horror, instead of doing something about it, I watched in horror as each row of people looked back and tried to figure out why their backpack had just been covered in Coke. And at the end of that, for some reason I didn't just say, excuse me, to the professor, I just spilled my Coke and it's going to cover everybody's backpacks. I just watched it happen, and then I never went back to that class. So in any case, don't do that. Alternately, if you do spill something, just raise attention to it so you don't suffer my incredibly bad experience, which I still, as you can tell, feel bad about. In any case, Like I said, what I was talking about were my own office hours. I do have my own office hours. I may add another one. The inverse property that has occurred is that the bigger this class gets, the fewer people come to see me in office hours. I think it's some sort of law of how could that guy ever have time for me in this sea of humanity? But just let it be known that generally my office hours are like dead quiet. I don't mind that because I have plenty of things to do, but I do also like meeting you. It's nice to meet people. I actually enjoy meeting people who are in this class. And so if you have the time or the inclination, please feel free to come by. If you can't make my office hours, send a time and send a note, and we can find maybe another time too. But of course, those probably can't accommodate all the questions that are needed to be answered. Okay, any other questions about that, or any questions at all about that? Make sense? Okay, and now we will go back to project one. To be done by yourself. Like I said, the first few will be like this, and then we'll pair up. First we'll talk about the project description, which is found it's just in GitHub somewhere, because I've started putting them there because people at other universities wish to you also use these things. So I'm finally trying to spend a little time on that. And then I'll talk a little bit about a few other things about how do you hand it in. And we did decide that there should be a little contest. So we'll talk about that too. Like I said, that results in the glory of winning as well as a t-shirt. So we'll talk about what that is in a second. Okay, so here is the description, which we will just read together. The first project is just about implementing a few Unix utilities. It's nothing complicated about it, excuse me. Sometimes people find the reason we do this as a project is sometimes people find, when you start to get, start to understand Unix, you understand it's knowing a lot of, sitting at the shell at the command line and then knowing a bunch of commands that you can string together to do very powerful things in very few lines, very, very little typing. At some point you start to wonder, well, you realize each of these commands are just programs that somebody wrote, like ls, that lists files. That's just a program that knows how to talk to the operating system, the file system specifically, and figure out what files are in a directory and list them, print them to the screen. Many other programs, right? All of these Unix utilities. So we're just going to write a few of them or some form of each of them as a way to start to understand how those programs work, as just as well as to remember how to program a little bit in C, and then finally how to program in C in this class so you know how to hand things in and get them graded and get the grade that you desire, which is of course a perfect grade, which is what you should get on this first simple assignment. Okay, so those are all our goals here. And of course you have to remember how to use an editor and all of those things. Some people are very used to like living in a world of an IDE of some kind. And so here you may not be, depends what your editor you're using, but also learning some editor where you can kind of be successful in the Unix world is a good idea. So we're going to focus on 4 simple utilities, basically cat, grep, and then zip and unzip, some form of compression, decompression. Cat just basically takes a file or a bunch of files and then just dumps the contents to the screen. Grep, if you've used it before, you give it a search term and a file or series of files, and it looks for lines that have that search term on it. We're doing a very simple form of that. And then zip and unzip, zip will take a file and then basically use a very simple compression technique called run length encoding to compress the file. Potentially, in some cases, it may make the file bigger depending what happens, depending on the contents of the file. And then unzip will undo that and essentially decompress the file. So that's the basic idea. Any questions about that? Does it make sense? Yeah, so, your enthusiasm is overwhelming me. So let's move on. Just a wall of nothing. Okay, it's hard to have an opinion on whether I'm implementing CAT or not, I guess. We will require that for all, and the testing that we do will require that you run with certain flags, particularly -w all and -w error. -w all means just we're turning on all the warnings of the compiler. We're basically making you pay attention to them. -w error turns those warnings into errors. That means it stops compiling. And then we will supply tests to you. I'll show you a little bit what that's gonna look like, how to run the tests yourself. I'll show you that today. We haven't released the tests yet, though. Those will be released If I were optimistic, I'd say tomorrow. If I were realistic, I'd say Friday. And if I remember everything that's ever happened in this class before, I'd say Saturday. So it's either Thursday, Friday, or Saturday. You'll get the tests. They're not going to be super grueling tests. They're just going to be basically if you read the spec and followed the spec, you'll probably pass the test or most of the tests on the first try. That said, where you will get complaints, and the test will tell you about this, is if you add an extra space somewhere in a message that we said to print out, and we that's what you're doing, the test will complain. It'll say your output doesn't match, and you won't pass a test until you fix that. Okay, so let's talk about and all the versions of these tools. Instead of calling it cat, we're calling it my whatever. So this quite silly sounding my cat is the first program that we'll do. So let me do this. I'll quickly talk about, let's just kind of get into some examples. So mycat, this is how you would run it. You would say mycat and then some file, let's say main.c, and then it should just kind of print out main.c to the screen using printf, okay? Like I said, here you see this kind of Unix shellism. We say // before mycat. Why are we doing that? Does anybody know? Sorry? Yeah, in Unix, when we type a command, and we'll learn more about a shell when we do a next project, or a few projects from now, we'll actually implement a Unix shell, and we'll learn about how when you type a command like ls, for example, like let's say I'm in a Unix shell and I type a command like ls, a provocatively named directory called solutions. What's in there? Let's look. No, we're not going to look at that. When I type ls, somehow the shell knows where this ls binary, it's a binary, it's an executable program, it knows where it is, and then the operating system runs it. It means it loads it into memory, and then it does those things we started to talk about a little bit yesterday in class, which is it starts to execute the main function of the ls program. But for some programs, there's only certain places that the shell knows where to look for programs. And when you're writing a program, it's going to be in your current directory is where that program lives. And a lot of times the way the shell is set up is it doesn't look for the binaries in the current directory you're in. And there's some security reasons for that, weak security reasons perhaps. So the way we're going to tell it where in the file system the binary is we're going to say it's in the current directory, which we refer to in Unix with a dot. We say the dot is the current directory. So if we say /mycat, I'm going to be assuming that there's a program called mycat in the current directory, and I want you to execute that program. Now, if I do that right now, what's going to happen? Nothing. Well, something will happen. It'll say, I don't know where that command, there's no such command mycat in the current working directory. We'll talk a lot about file systems in the third part of the course, but we'll learn a little bit about how to, if you're not super familiar with Unix or super comfortable, we'll learn a little bit along the way just in these kind of sessions that we do together. Okay, so let's quickly look back here. So what we're going to do is we're going to eventually compile whatever code that we write like this, and we'll look at this line in a second. And then the rest of this assignment is telling you is basically giving you some hints at some library routines that you can use in order to implement these Unix utilities. These are all part of the C standard library. As you may know, when you write and compile a C program on Unix-based systems, you are automatically linked with the C standard library, which contains a bunch of useful things that you can use to construct your programs. It's generally good to have some familiarity with the C standard library. Amazingly, this link I provided here is to Wikipedia, and is kind of a great link actually that covers a lot of what's in the C standard library. And they basically divide it by all these different includes, which you can include at the top of your program, and then inside of each of these it kind of tells you what are all the functions we can call that are relevant to that. Now, are you going to sit there and read that? Probably not, or not yet. But if you ever want to, that's a great place to look. And the more you know about what's in the C standard library, generally knowing your libraries and knowing the framework around, like you think learning a language is really, at first you think it's like syntax. But syntax is very easy in the end, right? It's, you place a semicolon here, a brace there. What you really want to learn to be effective in a particular environment, all the library routines, all the code someone else has written so that you don't have to reinvent the wheel every time. right? And so for C, it means you learn the C standard library and all the parts of it that might be useful in constructing programs. And of course, we'll touch on various pieces of that throughout class, but won't touch on the expanse of it in any way, shape, or form. There's a lot to learn that we won't talk about. Okay, so for this part of the project, MyCat, or our version of CAT, what I'm going to talk about is, sorry, I don't want to keep saying my cat because it makes me think of my cat, which we do have a cat. And so that's kind of a strange thing to be talking about in the middle of this class. So in any case, I'm going to say this version of cat. And what we're going to use to implement this version of cat is a few simple routines. We're going to use fopen, which is a file open library call, fgetS, which allows us to read from that file, and then fclose when we're done with it. The way we learn about these different routines, we of course can look at like a Wikipedia page about it or something on the internet, or we can simply use the man pages. And I'm going to encourage you to learn to use the man pages because they're just convenient and they're there. So let's say we type man fopen, for example. We might see a couple things, and this is how we learn how to read this. We see the synopsis at the top. You can see what, oh yes, this is in the C standard library like we were talking about. That's up here. Everybody can read this, yes, in the back? Yeah, okay. Otherwise, move forward. And then we see a few different calls, including fopen, and we can see in the synopsis part here, to use fopen, we want to include standardIO.h, hashtag include. Now, when I put a hashtag, isn't it funny that I said that? Usually I would say pound include, which is the kind of old way of saying that. But now people call them hashtags, and I found people understand me better when I say it's a hashtag. So yes, it's a pound include in my terminology. Anyway, what does pound include at the top of or anywhere in a C program do? How does that? What is that? What does that mean? Yeah, these pound directives that you'll see in C programs are actually not really part of the C language. They're part of something that runs before the C compiler runs. It's called the C preprocessor. The C preprocessor in and of itself is kind of a macro language. Pretty powerful, and it's very commonly used in C programs to do lots of different things. That what it does here when we do pound include is it basically says find the file standardIO.h and just kind of include it in this file, and then compile that thing, and maybe recursively include a bunch more files until you run out of directives to follow. So it's not like as powerful as an import statement or something more formal that might happen in a different language. It's literally just giving you more source text, which is eventually going to feed to the C compiler, which is then going to produce eventually, say, a binary executable. So here we know to do this. And then we're going to try to call, say, fopen, and then we can kind of read the man page here to understand the parameters and how to use them. Here it's pretty easy. We use a file name, and then we use a mode. Mode is going to tell us whether we're reading or writing. So let's just go ahead and, I guess, do that. Let's make mycat.c, and let's have I have a little macro here to just have a little C program. So that looks like that, and you can see I already included standardIO.h here, and so then we can cut and paste this line here and kind of use that as a starting point for our program. We want to open a file, and you see what we're going to get back from this nice library call is we get back a file stream, a pointer to this kind of type file, or what we call a file stream. So we're going to need something like a variable that is going to hold this reference to this file so that we can then later read and write the file and eventually close it and things like that. Now we're going to need a file name here. Pretty simply, that's going to come from the argv over here, and argv0 in general is what? Do people know? It's like the name of the program. So in this case, it would be mycat. So let's ignore that, or /mycat or something like that. So let's just assume we're passing in a single file name right here, and then we want to open it for reading. So as it said on the man page, put quotes, double quotes around an R, and go from there. Okay, so then let's look at the description a little bit better. You can see here one thing we were going to want to do is we're going to want to check if the file open succeeded, because if the file that gets passed into cat doesn't exist, we shouldn't assume, what we'll get back from fopen is a null, and then suddenly we start using that to try to do things, bad stuff is going to happen. So we should just go ahead and check what's going on there. And so here we just cut and paste that. And then, right now we can just say fclose, which gets, is done. And this is kind of a simple program that all it does is open and close a file. Okay, so very simple, and hopefully probably kind of review for most of you. So let's see if it works. Go ahead like this. And I said we should compile like that. Sorry. Okay, and I did one thing in here, which is a very readable error, actually. It says, hey, you're implicitly declaring exit. And in fact, it's telling you, hey, you know what you should be doing? You're trying to use exit, but you haven't included the right include file here to actually use exit. Exit here basically quits the program and then gives a kind of an error code of 1. It's very common in Unix-based systems for 0, an error code or return code of 0 to mean everything worked, and an error code that's non-zero to mean something went wrong, so we'll often use 1 for that. And so we'll go ahead and include standard lib.h here so we can, the compiler won't complain about not knowing what exit is. Okay, and it's a very common thing is what you kind of have to do to become good at debugging here is learn how to read what the compiler is telling you. The compiler gives you a lot of information, but sometimes it gives it in somewhat cryptic ways. I'm actually just running this on my Mac, so it'll be a slightly different set of compiler warnings and errors that I get than you'll get on the Linux-based machines that you're using. But more or less, you have to learn how to read that in order to become an effective programmer. So when you see something you don't understand, try to understand it. It actually is telling you a lot, and it will make you very effective at knowing exactly what the problem is. So let's try that again. So we get a clean compilation, and then let's say we say, let's also create a test file that we want to cat test.1 or something like that. Hello, this is a file about to be catted, I guess. Okay. So let's go ahead and run that on my test file, and you can see how exciting that is. It doesn't do anything because we just opened the file and we closed it. Of course, if we passed it test.2, what would we expect at this point? Yeah, we should say cannot open file. And it turns out the project spec is more or less it's exactly that. It says that you should print, actually I think it says you should print my cat cannot open file in the case where you can't open the file. Okay. So let's just look at one more thing and then be done with my cat, and then you'll be actually almost done with it. Amazingly, it's that simple. It's really a very gentle warm-up, perhaps too gentle. And so what we are just suggesting you can use here is fgetS to read in lines from the file and then use printf to print them out. So let's go ahead and do that. Okay, and the way we're going to learn about fgetS is we just again read the man page. So let's go ahead and read this. So you can see the fgetS takes a few different things. It takes a pointer to essentially a buffer to a pointer to it looks like a character, but it's really like an array of characters where it's going to read in some characters. It says tell me what size that is, so I don't try to read in more into that buffer than there is room for. And see, we're always very worried about, when we have a buffer, we want to make sure that we don't copy too many things into it. In fact, that kind of buffer overflow, as you may know, I think you probably talked about this in 354, is a very big security hole in a lot of C programs. That if you kind of allow user input of some kind to find its way into a buffer and you're not constraining that, eventually someone can overwrite the stack and they can inject code into your running program, and then when you return from somewhere, you essentially jump to their code and suddenly they've taken over your program. Huge security hole, still a problem for C-based programs. And then the third argument here is just the file stream that we opened a moment ago. What you can see is when you read the return values, what fgetS returns on success is a pointer to the string it just read in, and then if the end of file occurs, you get a null. So we essentially, one way we're going to read a file is we're going to go ahead and say read until we get a null back is kind of a simple way to think of it. So let's go ahead and let's make a buffer here of some kind, and let's go ahead and make it well, let's just be lazy and put a number in, and then let's go ahead and pass the file pointer fp, which we got from opening up here. And while it doesn't equal null, what we're going to do is simply, well, let's do a couple things. Let's go ahead and declare that buffer of that same size. And now, of course, what some people might do in a C-based program, they might say, well, I don't want to have the number 512 throughout my code, so I might call it like a buffer size or something like that. And then go ahead and define that with our C preprocessor. So we might do something like that, and then go ahead and know that anytime I want to change the size of the buffer, I can just change it in one location. That's a very common C-ism. And now what I want to do is I would just want to print out the value of the buffer that I just read in, and that's pretty easily accomplished here. Let's make this not quite correct. You'll see why in a second. Let's print out the buffer which we just read in. Okay. So let's see how this program works. Compiles. Let's mycat test.1, and you can see it's not quite right, because when we cat test.1, which is a good comparison point, you can see that we have put a bunch of extra new line characters in, because when we read in the buffer, the file into this buffer, we're also reading in the new line character that is in that file. And so when we print out an extra one here, that's incorrect. So we shouldn't do that when we're building cat, or our version of cat. Okay, so let's see if that works. And then we have, now I've mostly implemented the first part of this project for you. So you can see this is not going to be a terribly hard project, which is good, and you should feel relaxed. But you should know that we should not forget the theme of the course, which is it always gets worse. So the first one's the easiest. And like I said, if it's hard for you, it's going to be a rough sledding. So that's most of that. There's a few details you should look at to get right. We can, for example, it should be able to handle one or more files on the command line. So if there's a bunch of files, you should just cat all of them. You should output all of them. There's a question over here. How do you determine a good buffer size? That's a good question. It's surprisingly hard to answer. Usually people, because they're computer scientists, randomly pick powers of 2, like I just did, which is, to some sense, nonsensical. Eventually, things like that there'll be performance considerations. For example, if you read something like a file 1 byte at a time, that will cause more overhead to exist than if you read it, 1 big chunk at a time. So you usually want it to be big enough so that the overhead of calling the routine is kind of, you don't feel the cost of it. It's called amortizing the overhead of something like that. So big enough, but having it be incredibly huge isn't going to be super useful here, because we're using fgetS, and fgetS is just getting us a line back at a time. So I picked a number that I know is probably bigger than most line sizes. In this program, the program would work functionally equivalently. Like, let's say I made a buffer size of 2 right here. It's not going to change anything about how the program behaves, because we just read in 2 characters and print them, read in 2, print them, but it might be slower, right, if we have a smaller size. So that's something that's probably best determined empirically. If I'd picked 100, that'd probably be fine. Most lines aren't that long. Good question. And we'll see, as we get more into systems, how some of those overheads are things we care about. Good question? No, just a stretch. Stretching is a good question too. Okay, so let's just quickly talk about the other things. There's some details about, when a proper C program that terminates successfully should return 0. You can see that I did that in this code down here. You could also call exit with 0. That's a functionally equivalent. What we did is slightly different than cat, actually, is if there are no files specified in the command line, it should just exit and return 0. That's not exactly how cat behaves. You can figure out why that is. And then if we try to call fopen and that fails, it should print this message followed by a new line, and that's it. And our program example already does that. Now, some of you may know that in Unix-based programs, when you print an error message, you often don't print it to just the standard out, the standard use standard printf, use fprintf, and print it to something called standard error. We'll talk more about those things later, but for now, ignore that. And if you're kind of doing a slightly easier thing, just print it to the screen using printf. How many people have printed to standard error before? Okay, so some of you. So don't do that for this project. And we will do it in the future, and we will specify it exactly in the future, and that is more of a proper thing to do. Okay. So one thing I want to do now is I will show you how our testing software will work. I have a version on my computer. It'll be in a different location. It'll be on AFS on the Linux machines that you use with a different path name to it. So don't get obsessed with how I ran it exactly, but you'll just see kind of what it does, and then you'll be able to use it effectively. And being effective at it means running tests, and then you'll be able to know what the tests do and then kind of debug ones on your own without having to ask us what's going on, right, about the test framework. So we're actually kind of revamping the test framework a bit to make it simpler to understand, because in the past it had been a little bit challenging. Okay. So let me see how the testing will work. Testing, there'll be a testing directory. Binaries are often historically stored in a directory called bin, even when they're not in actual binaries, they're just scripts. And there'll be a test for each of these programs called test dash the name of the program. So there'll be test my cat, which sounds again like a veterinary procedure. There'll be test my grep, there'll be test my zip, and test my unzip, which actually just sounds weird now that I say it. So yeah, don't. So anyway, let's test my cat and see what this does. And you can see it does a few different things and eventually fails because I didn't implement the entire project. The first test will always be did your program have a clean build? So did it compile, and did it compile with no warnings at all? So we could, for example, ruin that by doing something like declaring an extra variable here and not using it. Good modern C compilers will warn you, hey, you declared J, but you didn't use it. So if we ran the tester, then it'll say clean build, result failed, and it tells you kind of, hey, that just didn't, the return code doesn't match or whatever. It says something's wrong. And then you might want to say, well, I want to then see what actually the tester ran in order to produce this problem. And so there's just a verbose flag -v that you can add to the testing framework. And we'll document all of this too when we release the test. There'll be a README that says all these things too, so you don't have to worry exactly if you're not catching it all right now. And then what that -v includes then is it includes this line, which tells the exact command that the tester ran, which you can then, for example, in this case, just cut and paste and run, and then see it says unused variable J. So we'll get rid of that. And then we can do the same thing and run here. And then here you can see the first test that fails is the simple multi-file test. And it says, you can see why it's failing, because basically it's catting two files and hoping that that works. And we know the program I just wrote doesn't deal with more than one input file. It just deals with argv1. It doesn't deal with all of them. You can imagine how you might solve that with our old friend, the for loop or something like that. But that's going to be perhaps the first thing you'll do in this. And then you can see here, where did the word child come from in that? I don't know. So I'm losing my mind. So what you can also see here is one of the outputs is it tells you what it expected and then what it got from your program. Here it says this line is from one file, this line is from another file. That's what it expected between the brackets, but it said I only got this line is from one file. So you have a lot of information that you're given about what didn't work by just looking at the output of the testing and understanding how to read that. Okay? Any questions about that? Yeah, it's a little bit of a simple project, so it's not too exciting yet. Okay, so let's just talk briefly about the other things you'll be implementing. Yes, there's a question.
Are the tests in order? Like if you fail test 1, you won't be able to use test 2 and 3?
Yeah, so the way we will run them is there's a different test mode called -C, which says continue all the tests even if some fail. And so, you can see all the results at any point. There's also a way to run a specific test if you want to just focus on that. But it's not like it builds in any way. Each one's just a separate test. You could pass 1, 2, 6, 8, and 10. Hopefully you'll pass all of them. But yeah, you shouldn't be worried. There's nothing dependent about them. Good question. Other questions? Yeah.
For like is failing one test mean zero, or is it like what is the
Hmm.
grading?
Oh yeah, how does the grading work? No, it's not all or nothing on the test. Like each specific test will be worth something. So if you pass 9 out of 10 tests, you will. I made it sound harsh, and I guess you're saying I made it sound so harsh that you're like, if I make any mistake, I will immediately be flunked out of school. So it's not quite that bad. It's just whatever test you pass, that's your score essentially, and it's strictly it'll be exactly proportional. Yeah. Oh, that's a great point. Thank you for being pedantic, but noticing a good detail. If you don't pass the compile test, you won't pass any of the other tests. It's true. So your test better pass the compile test, which means compile without warnings or of course, errors. Great point. Now, you will have the test framework, so it would be very surprising if you turn something in that doesn't compile and expect to get anything other than some sort of pity from us, which we do feel bad when that's the case, but yeah, you have to pass the compiler test. Great point. Good detail noticing. I was being sloppy. Other thoughts? Doesn't sound too hard, right? Okay, so the next tool is grep. Grep, if you haven't used it, you say like grep and you look for, say, a search term like foo in the file bar.txt. So this line has foo in it, so does this foolish one. Even this line, which has bar food in it, will be printed. So all of those would match. Other lines that don't have the characters FOO right in a row would not pass. So you can imagine that's going to look, the flow of that program is going to look a lot like your cat program, except you're not, it's essentially a selective catting of the file. It's on each line, you're basically saying, does this line have, you're doing a test, does this line have the string in it? And if it does, print the line, otherwise don't. That's all grep does. And grep has a lot more fanciness to it where you can do patterns and, expressions of different kinds. Here we're just doing straight, exactly the characters that you type, do they match? And it's case sensitive, so if it's different capitalization, it shouldn't match, et cetera, et cetera. So that's grep. The one tricky part, which actually isn't that tricky, is lines may be arbitrarily long, which is if you look at the code, the way we implemented our version of my cat right here, if you look at that, this would be a little bit tricky to deal with long lines because let's say we think 100 is our max line length, and then someone gives us a line that's a length 1,000. We'll call fgetS 10 times on that. So if you're doing like a check on each little chunk of that line, you would print out chunks of that line based on whether they had the string instead of the whole line, which is what you should do. So the first challenge would be, how do you deal with arbitrarily long lines? Unfortunately, somebody has already dealt with this challenge for you in the library, which is now a standard part of C standard libraries, didn't used to be. And instead of making you not know that and suffering, I just decided to tell you about that. So instead of using fgetS for this part, you should look into using getLine. GetLine is a little more complicated to call, but not very complicated, and actually does this for you. It basically reads a line and it keeps reallocating memory until it can fit the whole line and then gives you back that thing. And then you have to free it when you're done. So use that perhaps instead of fgetS for this part of the program. And then there's just a bunch of details about little errors you have to deal with. One other thing you have to do with grep is you have to be able to read from not just files passed in, but if no file is passed in, you have to read from what's called standard input. Every Unix program that's running has a few file streams open by default, or for you to really file this, what look like files, but really are just allowing you to kind of interact with other programs or the screen. So standard input you can read from, and that's input that's getting sent to this program, and we'll show how that's done in a second. And then standard output and standard error are where essentially when you call print, what we're really doing is we're just writing to those file streams, and then it ends up on your screen. Now, what reading from standard input looks like, by the way, when I say reading from standard input, how many people are like, I already know 100% what you're talking about? Okay, great. I can never tell what's going to be useful. So, like if I type grep, let's say, let's make a test file. Oh no, we already have a test file. What's it called? Test.1. Okay, so let's say we did grep and we did this on test.1. We would expect to see this as a file because that has the string this in it. That's how grep works, and that's how your mygrep will work. If we try just grep this without specifying any files, it just kind of hangs. Now, sometimes people report this as a bug. It's not a bug, it's a feature. And what it means is the grep, this has literally been reported as a bug. Like grep doesn't work. When I don't pass it a file, it hangs. No, that's not correct. What it's doing right now, it's reading from standard input. It's waiting for me to type something to it, and then it's going to do the grep over that. So if I say hello and hit enter, it does nothing. If I say this line, it says this line. And then when I'm done, what I want to do is figure out a way to send an end-of-file terminator to it. There's kind of a hack in Unix systems where you type Control-D, and then it sends an end-of-file, and we stop reading from standard input. That's very cool, except not super useful. Where it's useful is when you do things like, let's say we did ls-al or something like that. So ls lists files, -a-l gives a lot of information about the files. And then we want to, for example, look through a long listing for there's some solutions in this listing that we're interested in. What this line does is it's called a Unix pipe, and what it does is it takes the output that's being printed from ls, and it sends it to the standard input of grep, and then we can string together these very powerful kind of meta programs, which is where much of the beauty of Unix originally comes from, is the ability to string these commands together with these things called pipes. How does that all work? We'll learn in about a couple weeks. But it's pretty cool, and it means, if you think about it like this, we didn't change anything about the program ls, we didn't change anything about the program grep, but we can string them together and make them work together with this very powerful pipe abstraction, which is just a vertical line right here. So anyway, lots of cool stuff about the Unix shell, which we'll learn about. What you have to do is figure out how to read from standard input for your mygrep. It turns out that's super easy, because in programs, Unix programs, there's already a file stream open called standardin. It's defined in standardio.h, that include file. So instead of using fp like we did before, you can just use standardin and read from that. You just have to figure out the logic of when to read from that instead of reading from fp from a file that you opened. Does that make sense? If not, it will make sense at some point. Okay, any questions about that? Yeah?
I was wondering if you're going to share that macro.
Share which?
That macro that you used to just create a simple receipt program.
Sure, I could share all that stuff with you. Everything that I do is within Emacs, so it's only going to be useful for people who are using Emacs. And then, it's a lot of just like eLisp code that I wrote over some years, and it's pretty, ugly. But sure, I could share that with you if you want. I don't know how helpful it would be, but sure. We can do that offline. Okay, so let's do a couple last things. Just one last thing, really. There's one last little program down here, which is they're kind of a pair of programs, myzip and myunzip. So zip, what it's going to do, it's going to take like a file like this, with a bunch of A's and a few B's in it. And then logically what it's doing, it's going to turn that into a compressed form, which says, there's 10 A's followed by 4 B's. And you can see if there are long runs, this is why it's called run length encoding, is when you take a long run of the same character, you can compress it to a number in one character. So that's a compression. And then the unzip does the opposite of that. It takes this compressed format and then expands it back to its original version. Okay? Now the only tricky thing here is we have to understand the difference between text encoding and binary encoding. And so when we're writing the compressed form, we're not going to write text 10, 1, 0 like we were, printing. If we print 1 and 0 or the number 10, %d, a number, that's going to print out ASCII text. The requirement here is that you encode that as a 4-byte int in binary format. And so let's make sure we understand the difference between those two things. So for example, if we cat that file that we've been using so much, this is, when cat is treating this data as ASCII. So for example, if you look at a hex dump of this file, you see all the ASCII characters of, all the ASCII codes for each of these, H is like, lowercase h is 68 and lowercase e is 65, etc., etc., etc. When we're writing binary, we're doing something quite different. So let me maybe write a little program that does something like that. Binary.c or something like that. And then let's go ahead and, well, we have a lot of stuff in mycat.c already, so let's go ahead and use that. Instead of reading, let's write, and then let's go ahead and show the difference between writing ASCII and writing binary. So when we, for example, when we're writing ASCII, we would just say, let's say we wanted to print out a count, which is what we're printing out actually, right? In our encoding, we have a count and then the character. So like how many times does this character appear, and then the character. So let's say the count was 33, and then we go ahead and print out this character in just, like this, okay? And why are we opening anything? We don't need to do any of this, actually. Yeah, that's fine. Okay, I'll just do it like this. This is easiest. Okay, so we go ahead and print that, and if we print it to a file, let's call it out.1. So if we cat this file, we see 33, and you can see there's no new line there because we didn't print a new line. But if we did a hex dump of this file, hex dump just shows you the exact, what's in there in binary. We can see, that's a bit funny. I picked a funny number, actually. So let me print something else. Count as a 99 or something like that, or a 91. So what we're seeing is some encoding of 9 and 1, the characters, right? So each ASCII character. What we want to do when we're encoding, when we're writing out the character in binary format, is we want to use a slightly different routines. So fread and fwrite will allow us to read and write in binary. And if we're going to read fwrite, and we're kind of running out of time, so let me end on this. I'll try to treat this like it's a 50-minute class or 1 hour at most. What you can see what fread and fwrite do is they take the thing you're going to write, how big it is, how many of those things there are, and then a stream to write to. So, let's just go ahead and cut and paste that. And so we want to write out the integer in its binary format. How big is that? Well, the integer we know is a size of an int. We use the size of operator in C to do that. How many ints do we have there? Is it an array or is it just one? It's just one. And here we want to write this. In this case, let's just go ahead and write it to standard out, which is one of those streams that is already open for us to write to. And we just type standard out for that. So this is going to write one binary integer to standard out. Let's go ahead and write that. Instead of writing it to out.1, let's write it to out.2 so we can compare the two. So here when we do a hex dump of out.2, you can see there are 4 bytes written, and then this is, that's the actual number. It's in hex instead of being in, like looking like a decimal number. And then you might notice also those 4 bytes are kind of written out in funny order. x86, which is what I'm running here, stores data in little endian format. Do people learn about that in 354? Little endian versus big endian format. So it's just a way of when I have like a 4-byte integer, where do I put the least significant and most significant bits? Do I put it left to right or right to left? And this is the way x86 does it. You can see how different that is than the text we printed in the previous version, where it just showed 2 characters, quite different contents. For this part of the project, you have to get that right. Last piece on my zip is, there's some other recommendations here about how you should do that. But the challenge is the contest, if you're interested in spending more than a little bit of time on this project, is to make the fastest zip. And so that's the only instruction we're giving. We'll give you a very large file to try to zip, and then you're going to have to figure out how to most quickly compress it. What you can do for that, figure out whatever you want. There's no limits on that other than, tell us how to compile it, I guess. Okay, so I don't have anything else at this point. The test will be released soon. We have hours on the web page where TAs and peer mentors will be around. Send help requests to 537 help. And otherwise, enjoy the beginning of the semester.